So today's talk we have Elena Garcés, that she will be talking about her work in the startup, or probably it's no longer a startup anymore, SEDI. Well, a little bit of Elena. Elena did her PhD here in Universidad, Zaragoza, in the graphics group, where she interned twice in Adobe too. After she finished in 2017, she did a postdoc in Technicolor in Rennes, and and then when she finished that postdoc, she joined at Universidad de Juan Carlos in Madrid as a postdoctoral researcher, as a Juan de la Cierva Fellow, and then also as a technical scientist, as a research scientist at SEDI, at the startup SEDI, where she is now a senior researcher and tech manager in that company, which is a company that focuses on, well, all the pipeline aspects of digital clothing and fashion for fashion industry. So yeah, Elena, whenever you want, it's all yours.
Okay. Well, thank you very much, Adrian, for the introduction. And thank you all for inviting me to this research seminar. To me, it's a real pleasure to be back in the University of Zaragoza 4 years after I defended my PhD. Yes, Adrian said, I'm technical manager and senior research scientist in a company named SEDI. And in this talk, I will present who we are and what we do, and a bit of science about the problems that we are trying to solve. Hopefully, by the end of this talk, you might consider applying for an internship, a job, or maybe you just end up with a bit more knowledge about the existing challenges in garment digitization. So, first of all, SEDI is a startup. Well, probably not a startup anymore, but we are based on Madrid and Canada. Although we have now several people working remotely, given the situation. The company started as a spin-off of the MS Lab group of the URJC, led by Professor Miguel Ángel Otadui, with a huge expertise on mechanical simulation. They founded the company, I believe, 3.5 years ago. And at the beginning, they were maybe 10, 12 people. Now we are around 40, with a bunch of PhDs with diverse sets of skills, including mechanical simulation, render, computer vision, machine learning, as well as brilliant engineers that are helping us, are helping to make the tech become a real product, and also great product managers who lead the marketing and product strategy. So we are a real company now. So this is us, this is part of the team, and now I will tell you about what we do. So fashion is a huge but very inefficient business. Many items of cloth are simply trashed, either in the design process because they are never sold, or because they are returned by unsatisfied customers. Fashion production makes up 10% of humanity's carbon emissions and is the second largest discharger of wastewater. Some people say it's the second most polluting industry in the world, and I'm not sure that is super clear about this ranking, but fashion, it is certainly among the top 10 most contaminating industries in the world. So, what can we as engineers, as computer scientists and researchers help to change this situation? Well, this might surprise you, but fashion, the apparel industry, as opposed to other industries like the automobile, for example, lacks well-established digitalization workflows. Most of the processes are physical, from the design of the garment to any of the customer interaction. So the goal of SEDI is to provide the necessary tools that will make the transition from the physical to the virtual world more effective. Otherwise, it won't succeed, as this has happened to date. Before moving on, I would like you to think for a second about what makes garments particularly challenging to digitize. So let's focus on this dress and let's focus on the individual pieces that compose it. So first, we need to take a look at the raw material, which are textiles. Textiles are for a garment designer what, let's say, crayon pencils are for a painter artist. This means that textiles need to be very well understood so that the creative process can take place, as well as the predictable editing. So for textile data, we might face information like the color of each yarn, the finishing applied to the fabric, or other properties like the twist of the yarns, the amount of flyouts, or physical properties like the weight or the yarn count. So the second element to create a garment is, once we have the fabric materials, are the patterns and the sewing data. So once we have fabrics, we need to figure out how we compose this fabric into the patterns to make the garment. In this sense, we have information about the building, the construction of the fabric regarding, for example, the sewing order, the stitch and seam type, the stitches per inch, thread type, whether the fabric might have interlinings or finishings, any kind of trim that the garment might have. So we need to have all this information that compose the actual garment. No? And finally, the last piece of this problem of bringing full virtual pipeline into digitalization is the fit data. We might create a garment, but we need to know, I mean, this garment needs to be used, right? So we need to figure out how this garment fit into our body. So we need to know which areas compress. We need to know an accurate grading to different sizes of the avatar. The garment needs to have proper draping according to movement, if the avatar moves, and so on. So these are the three key pieces that will, if we have them, we will be able to bring digitalization into the fashion industry. And this is our goal. In SEDI, we have an integral solution for these three pieces. Our goal is to make digital twins a real thing. As opposed to other software packages, which are meant only for visualization purposes, our purpose is more to understand deep into the physical properties of the fabric, into the real construction of the fabrics and the garments, so that we can provide the tools that will allow predictable engineering. So we provide yarn-based simulations and renders. We provide tools that enable accurate patterns and seams constructions, as well as we provide a technology that will enable soft avatars, which is what really happens in the real world. You might wonder, what does it mean? What means soft tissue avatar? So when you think about avatars and mannequins, these are usually rigid, right? And you put the garment on top, and this is not realistic. Our bodies are soft and they deform with the physical, when we apply physical forces to it. So when I mean soft tissue avatars, I mean this. I mean a technology that will deform the body as well as the clothes, taking into account the actual physical forces that exist in the simulation. So this is still a very research. This is still in a research state, but this is the kind of realism that we would like to provide as a company. So today, because I cannot talk about everything, I wish I could, but I can't. There is not enough time. Today, I'm going to focus on the textile part. I'm going to talk about which are the challenges and problems and how we solve them for digitalizing textile materials. Okay, a second. So to start talking about that, and because this is a master course, I'm going to talk a little bit about rendering and physically based rendering. How do we reproduce materials with a computer? And to this end, we need to start from the beginning. So how do we render a material with a computer? To know the color of a point in a surface seen from certain direction, we need to know how much light this point reflects. This amount is given by the amount of light that reaches the surface, as well as the amount of light that is absorbed and reflected by the material. So in classic render theory, this process has been modeled many times with the Cajilla's render equation, which I'm sure you have heard about that. If not, you will for sure in this master. So essentially, this equation says that the amount of light that reaches our eye is the sum of the light emitted by the point, which this only applies for light sources, plus the sum for all the directions in the hemisphere of the product between the proportion of light reflected by the material times the incoming light attenuated by the cosine law given by the Lambert equation. So this is a simplification of the real world. This doesn't even take into account more complex effects of the light. But I think it serves for illustrating the purpose, which is to illustrate the complexity of this process of rendering. So after applying this equation on all the points of the surface that we want to render, we will obtain our image of the target scene. This process is what we have been doing in render for years, define these mathematical equations, but it's not the only way. For example, recent neural rendering techniques use neural networks to compute this strip of light along the space and inside the material. And thanks to the pre-computation of certain parts of the render equation above, neural networks can provide hyper-realistic images in almost no time. The problem with these techniques is, although we gain speed, we might lose interpretability and editability. It happens many times in these problems. Neural rendering is not going to be the focus of my talk, because what I will tell you is more about modeling the particular equations using classical rendering, but we plan to use neural rendering for a certain part of the pipeline. In any case, a common denominator for both techniques is that we need to know in advance the scene that we want to reproduce. Or in other words, we need to know the light, the materials, and the geometry of fabric materials, right? So let's try to take a look at fabric materials. What do they look like? Well, before I started working on this topic, I'm really not a render expert. I had heard that fabrics are one of the most difficult materials to render, and I think it took me 1 month to understand why that is the case. So the variety of fabrics that we can find in the market is pretty much infinite. I believe like humans' imagination, and its appearance depends on multiple factors. One factor is, for example, the relationship between the chemical dye used to tint the fabric and the fiber origin. For example, for the same dye, a natural fiber like wool or cotton will produce a different color than the same dye applied to an artificial fiber like polyester. Another factor that affects the appearance is the fabric structure. Whether it is a knit or a woven will affect the final look. And not only that, fabrics are almost always subject to particular finishings that change its appearance, touch, or performance. For example, denims are often treated so that they have these aspects of used or old, and also to have a more flexible and soft feeling. So we need to also take into account this processing that people do to the fabrics to have this final look that we see. No? So for a given fabric, how do we see what's going on? Can we tell only from these pictures, which is the woven structure, which are how the fabric has been dyed, or which are the parameters required to render this? I guess not, right? So what we need to do is a little bit more deeper into how the fabric is being made. And if we go deeper, we start to get the feeling, we start to get to understand why fabrics are so hard to reproduce in a render. So here we see a microscopic capture of a woven fabric. It seems to be a plain pattern of 2x2 yarns, and each yarn is composed of different types of fibers. I know it's wool because, well, the web page said so when I downloaded it, but I'm not fully sure. The fibers are twisted to form the yarn, and this twisting is not very tight because we can see a lot of flyouts that escape the main yarn. And this is essentially some technical details that compose the fabric at the micro level. And then having these pieces, I would like to pose another question, no? Like, which are the pieces, what do we need in order to render this material, to simulate this material with a computer? So first, we would need to model the light scattering inside the fiber, which is going to give the color, part of the color at least. Then we need to model also how the fibers are organized inside the yarn. Next thing is we need to model how these yarns are organized inside the fabric, because they usually have complex structure, complex patterns. And finally, we need to model the interaction and friction between the yarns when they are subject to external forces. You can imagine if the microgeometry is this one, the yarns are not tied to each other, they can slide. So modeling all these forces is really a very hard process. And not only that, even if we have these forward models, we still need to obtain these parameters from physical samples. So how we do that in SEDI? So we have a solution to capture and reproduce both the mechanical and the optical properties of the fabric materials. So we can digitalize and properly render real fabrics. For mechanics, we need to physically test and capture the parameters of the simulation model. In this proprietary machine, we apply stretching and bending forces to the fabrics and use both physical sensors as well as computer vision techniques to get the raw data necessary to fit the parameters of the simulation models. Our mechanical simulation models work at the yarn level, and thanks to this approach, we can capture the nonlinearity and anisotropy of fabrics, which determine the draping, folding, and wrinkles. The output of the mechanical simulation is a mesh geometry of the fabric. That is one option. The other option is what we see here, the final mesh, no, the geometry. The other option is if we work at the yarn level, the output will be the crossings that will define the yarn intersection. It depends on the accuracy, the model that we choose to reproduce the fabric. Currently, we have two models, one that works at the yarn level and another one that works at the more like a surface level. We are currently building a database of materials so that we can understand this relationship between simulation parameters and the physical draping and start applying machine learning to that. At this point, we have already filled one of the pieces that we said were necessary to render a fabric material, at least one of the pieces that work at the garment level, which is the geometry. So the next step is to define the material and its response to the incoming light. And for that, for this optical appearance, we have built our own Gonier reflectometer, which captures the optical appearance of the fabric while illuminated from multiple directions. In particular, we have here 130 LEDs, I believe, 31, of directional lighting, as well as backlighting, and also diffuse light illumination like the one we see here in the picture. Also, the device has 4 different cameras which capture the fabric sample at 3 different resolutions. I will show you some pictures later. In addition to that, we have the holder where we put the fabric to be captured. It's movable. I will show you now why we need that. So the first prototype was built by the Grupo de Tecnologías Fotónicas here in the University of Zaragoza, and it was pretty huge. This is very fun, but this guy is called the prototype the Death Star, like the Estrella de la Muerte, because it really looked like that by then. Right now, we have a more productized prototype, which is more robust. It has been built by a company also based in Zaragoza, which is called Aragon Photonics. And we are close, and this is this prototype. Let me show you this one. This prototype, we are building a second one right now. We are starting to define a second device. And key to this design is a camera that allows us to capture the fabric at microscopic resolution. Let me show you some images. So this is satin fabric, sorry, and each of this pixel is 1.8 microns. So, okay, you cannot see this kind of resolution with your own eyes. This is beyond your sight. Each of these yarns, each of these satin yarns has a radius width of 50 microns, which is amazing. It's like what we can see with a microscope. Here we can see another example of a fabric capture where we can actually see the flyouts. We can actually see the fibers that escape the main yarn. And we can actually see fibers that do not belong to this yarn, actually. I'm going to show you now some of the more images taken with this device. These are microscopic albedo image, which has a size of less than a square centimeter. And as we have backlighting, we can capture the transmittance effect. And beside, well, this is raw data taken with our machine. When essentially we take pictures of the fabric illuminated from each of the LEDs. And we have a couple of cameras that take pictures at the grazing angles so that we can observe anisotropic effects of the fabrics. And finally, we have another camera which captures a bigger sample of the fabric at macro resolution and also illuminated by backlighting. And what we see here is that, well, the macro resolution is more what you are used to see. This is a linen, so this is what you would consider a linen. But I guess you didn't imagine that a linen observed at this micro resolution would look like that. At least I didn't at the beginning. So it is pretty amazing how the fabrics look like when they are looked at the microscope. This makes rendering a real challenging task. And what do we do with this data? These data are raw images, but we can compute a set of physical layers using classical computer vision techniques. Let me explain. A very interesting feature that we have with our capture machine is that we leverage polarized light to isolate the specular highlights. Let me explain this. A light is a wave which in its raw state is unpolarized. So if we put a polarizer in front of the LED, we can force a polarization state of the light, which is what we see here. In this case, we may say it's parallel lighting. So for certain conditions of the material, what happens is that the first bounce of light, when it hits the surface and is reflected, it keeps the polarization state. So if it has parallel polarization, when it is reflected, it will maintain the original state. So if we put here in front of the lens a parallel polarizer, in this case, we will allow the reflection to pass. This happens for the specular highlight, for example, for metals. The first bones will reflect the light this way. And this will also happen for the reflections that are subject to a single scatter. What happens for other phenomena of light? So in this case, for materials that might have multiple scattering conditions, what happens with the light when it enters into the material is that it is subject to multiple bounces into the material, and these multiple bounces inside the material makes that the polarizing state of the light is depolarized. So the original state is lost. And what we can do here is to put, again, if we put a filter in front of the camera, we will filter part of this light wave and keep only what interests us. And you might wonder why we need that. Let me continue. With this idea in mind, what we do is we put a filter in front of each LED of the machine to filter the perpendicular component of the light wave, allowing it to pass only the parallel state of the light. And then, because our microscopic camera has a motorized polarizer, that means that we can control the polarizing angle of the camera, we can change the angle to two states. In one state, we would allow to pass the parallel reflection, meaning that what we capture is the sum of the subsurface scattering diffuse component plus the specular component, and we get an image as we see here. If we change the angle on the polarizer and we switch it 90 degrees, what happens is that we will blocking the perpendicular, we will blocking the parallel direction. We will be blocking the specular reflection, having only here the diffuse component. So what can we do now? Well, if we subtract these two images, we will end up having a pure specular image, which is incredibly useful when we are trying to render the material to fit the parameters of the render. So this is one of the physical layers that we compute. Another one is the normal map, and to compute the normal map, we use classical photometric stereo techniques, and using the diffuse state of the light where the speculars are filtered, we can pose the problem as assuming that the material is Lambertian, which makes our life much easier, whether we cannot do this as easily with specular materials. But we can do that thanks to this polarizer filter in the camera and the LEDs, and we can compute a normal mapping just by using the Lambert law and solving a system of equations. Besides that, another interesting feature that we compute directly using classical methods is that thanks to the density, the huge density in the sampling of the LEDs, we can trace the direction of the fiber. And by tracing the direction of each of the fibers, we get to understand the twist of the fiber, the twist of the yarn, which is a very important feature which determines how the material will look like. So at this point, we have our optical capture machine, and we have some raw data, which means that's raw images, and we have some physical layers computed given this raw data. But this is not it. With this data, we cannot render the material. We need some models that the computer can understand to render the material. And in this case, we have two models for render textiles. We have a yarn model and a surface model. And the final piece for making everything work together is that we need to fit the parameters of each of these models given this raw data. So let's focus now on the difference between these two models. Maybe you have already seen that in one of your render classes. So when we model the materials as a surface, we are making certain assumptions about the nature of the materials. For example, in this case, what we say here is, okay, when for a material that is modeled as a surface, the light will only hit the surface, and then it will be, part of the light will be reflected and part of the light will be absorbed and reflected again. And this model works pretty well for solid materials, for example, for wood or for plastic, for materials that doesn't have any transparency because nothing escapes, the light doesn't escape the material. So it works. What happens with fibers and with yarn? So if we take a look at a single fiber, what we see is that the light that hits the fiber, part of it will be reflected as in the surface model, but part of it will be transmitted. And we need to take into account that we not only have a single fiber, we have a stack of fibers twisted together to form a yarn. So if you do the maths and try to compute the classical path tracing operations where the ray is traced and you compute all the bounces of light around the material, you can imagine that this process is very costly to compute. It's very hard to do. But, well, it's more accurate to the real world. So if we have the surface model, it will be more efficient, of course, less expensive to capture, but we will lose a bit of realism. While for the yarn model, we lose efficiency, it will be more expensive to capture, but the realism will be much more closer to the reality. We need to take into account that when we are doing rendering, we are always approximating the reality because the optical process that happens in real world are super complex. So for the yarn model has many different parameters. For example, we need to take into account the shape and thickness of the fiber, the density, the amount of dye inside the fiber, more geometric properties like the shape of the cross section or the twist, and other optical properties like the roughness or the index of refraction. In practice, there are three pieces that we need to model to render with yarn. One, we need a scattering function, as I showed you before. We need to understand how portion of light is reflected by the fiber, how portion of light, how much light is absorbed by the fiber, and which part of the light is reflected back, as we can see here in this image. And each of these bounces, as we see here, the reflections, the bounce that is transmitted and the bounce that it is reflected inside the fiber and then gets out, each of these bounces has a particular parameter that we need to estimate. And this only for one fiber. But in practice, we not only see a single fiber, we see a yarn, and a yarn is built of fibers, no? So what we have for rendering yarns is a procedural model which, given some parameters of how the fibers are located inside the yarn, it generates infinite yarns very, very fast that are very close to the reality. And finally, now this is the geometry. I mean the geometry, but I should say more like the microgeometry when we deal with the yarn model. And one way to know this information, I mean, what people has done before, is to use CT scans to understand how the fibers are packed inside the yarn, because this information you don't know a priori. What we do in practice here, because these X-ray scans are super expensive, we observe the images that we take with the microscopic camera, and we sort of approximate what these parameters of the yarn are. And finally, because analytically render all these yarns and all this fiber is not feasible, what we do to render this model is to use volume rendering, and so we voxelize, we discretize the surface into voxels, and by computing these statistical functions about the voxel, we can render the material in a more cost-effective way. And here we have several results that were obtained with this yarn model. And the results are pretty impressive. They look super realistic. And we can even see the fibers leaving the surface. We can even see the flyouts that go out from the surface. You can see it here, or even in this fabric, green fabric on the right. The problem, sorry. So the problem, as you can imagine, with this yarn model is that it's a little bit inefficient, no? Because we need to generate all the yarns for a fabric, and a fabric might be as big as a dress or a curtain. So if we need to generate each of the yarn model, requires to generate and to model explicitly all the crossings between the yarn. And if these yarns are very small, the problem explodes computationally. So what we have instead is a surface model. We pivoted to this surface model, which enable faster renders and faster parameters estimation. And in particular, we use the Disney 2015 because it accounts for transmittance effects, which are pretty critical for rendering transparency and complex materials like hair. Now, as opposed to the yarn model, which had parameters per fiber and yarn, we have stacks of images, each one defining a particular parameter of their render function. Generating texture stacks, apart from the simplicity in generating them and capturing them, has an extra benefit over the yarn model, which is material compatibility. So this problem is something, if you're at the university, you sometimes never care because you have your models, you have your material, and you just do your thing. But if you're a company that digitizes materials and you would like your materials to be shared by existing software, not only yours, then material standards and compatibility might become a real problem. So in the apparel industry, there is an initiative to create a standard for fabrics. And this standard covers both mechanical parameters and optical parameters. And for optical, it is based on the Disney 2015. So here is another interesting reason to adopt this model instead of others. The problem with this standard, let's say, is that this standard defines the parameters, and these parameters are just names. And this standard doesn't define the mathematical equations that are required to use these parameters to render an image. So these mathematical equations is something that each render engine is the secret sauce, no, of each render engine. Nobody wants to share it. So this is here in the community, this is a problem that currently we are trying to deal with. So let's say we want to obtain the materials for a surface model. Next question is how? How do we get them? How do we estimate these parameters? And depending if you have been familiarized with the literature in computer graphics for material estimation, in the last, I would say 4 years at most, the amount of papers that aim to estimate this SBBRDF from with simple capture devices has grown, I mean, exponentially. I mean, there are many papers right now that try to get these parameters with simple acquisition systems. I recommend you to take a look at this survey, which captures pretty well what has been done so far. But I mean, there is another SIGGRAPH Asia paper which essentially does the same, with a mobile phone, but a little bit better with generative networks. So one option for us could be to use this approach and to use directly this implementation with the material, with the mobile phone scanners. But there are two problems here for us as a company. We depend on a database of a pre-existing database of materials that needs to exist. And in our case, because we are dealing with very complex materials, this doesn't exist. So if you take a look at these papers, they usually deal with generic materials like wool or plastics or stuff or metals, stuff very generic. But we need our more personalized, let's say, a database of materials with textiles materials. And the other problem that have these projects that rely a lot on machine learning and deep learning is that you are in principle attached to a single shader model. So once it is trained, it cannot be extended. So these are two problems. Besides these two problems, we have the problems that in order to generate this database of materials, we need to still fit the parameters at least once, to generate a faster way later. So we are on our way to build this database of materials. And how do we do that? For estimating the parameters, because we cannot rely on existing data, what we have is our microscopic captures plus the physical layer that we estimate. And what we do is classical optimization techniques to estimate the parameters of each shader model, either if it is Disney BSDF 2015 or if it is a more simple model like the BRDF 2012. And the output of this are microscopic texture maps. But these texture maps, I mean, you cannot render a fabric with only less than 1 square meter of material, because when you look at it, it won't look real. We need bigger samples. So what we have is a solution based on deep learning to propagate the data that we capture at microscale to an image that is captured at a microscale. And this is done with deep learning techniques. I won't get deep into that, but we have a patent and a paper pending about this topic. So yeah, maybe be able to talk about that more in the future. And the output of this process will be the SVBSDF or the SVBRDF at the macro level. And this, in principle, would allow us to render the material, right? Are we finished? I don't think so, no? There is another problem here. If we capture this sample of the material, let's say this is an 11 by 11 sample, and if we try to use this texture on the render engine, what we see is that if we tile the material in a 2x2 grid, as we can see, what we see is that the boundaries between materials we see them, right? This is not realistic at all. If you try to create a hyper-realistic image, it's not going to work. So what we need to do is to take the original texture and make it tileable. And this is really a very, very hard problem. And the graphics community and image processing has been dealing with this for many years. And it's not that there is a unified solution. Usually you take a look at the texture and then you choose one algorithm over the other because you feel that it's going to work better. So what we have in our tech is an automatic method that, given a texture and using neural networks, we find the minimum tileable tile so that when it is concatenated, we don't see the seams. And this is also patent pending and paper pending. So hopefully I will show you how we do that in the future. But the results look pretty impressive here. This is what this material would look like if we are trying to just stitch together the material as is. And this is what we obtain with our method, where the seams are actually not visible. Here is a 2x2 tiles of the basic material. And this closes our pipeline of generating texture materials, texture stacks. And with this pipeline, we try to get a little bit closer to this goal of making digital twins become a reality in terms of course, textiles, no, and yarn-based rendering and textile materials. Of course, we need these other pieces here, which are also super critical. Now I will show you some of the cool results that we are generating. And here we are combining optical and mechanical information of the fabrics as they come from the capture processes and estimation algorithms. These materials can be used to render garments of different colors, different properties. Here, it is important to notice that all these materials, we know the physical sample of this material. This is not something that an artist has said, oh, I'm going to put another more transparency in this t-shirt. No, this is something that we have captured with our machines. And the same for mechanical simulation. No? The wrinkles of these fabric materials are not the same as the wrinkles of this other one. And finally, another very cool feature that we have is the ability to render physically based stitches. And this is something that none of the competitor software has. So we can actually recreate true seams as they would be used in real world. And to finalize, I think I'm pretty done with the tech. I'm going to show you a video of a tech demo about our, because I have shown you the tech, no? But this tech doesn't work alone. We have two products that leverage this tech to provide some business value. So I'm going to show you let me see if we have time to show the two videos, but this is the video for the author tool. Can you hear it? Well, I will put the.
I think the sound doesn't.
The sound plays or not?
No, it doesn't.
Okay. Well, if it doesn't, I will pass it twice speed, because if not, you are going to be very bored. So maybe by 2 it works. Let's try. Okay. So this is a cloud-based tool which works on the browser. Everything that we provide are cloud services, and all the infrastructure required to run these services on the cloud is pretty impressive. So we have two views for the garment. One is a real-time view, and another one is a path trace image, as we will see later. And this is a tool for the garment artist, garment designer, that can really put in place all the pieces necessary to get this realism, this physically based construction of the garment. For example, here we can see the actual stitches. So here we can see the different seams and the order of the seams, because the order in which you stitch the pattern, it's important. And these are some final results after the path tracer has converged for enough time. And thanks to these true seams, and this physically accurate garment construction, we can change the, for example, the stitch type and see what it will look like. And here everything is physically based on capture parameters. The draping is simulated, and here the same. So if we change the fabric, it will also change the drape. So we provide some more information too about the fabric, the cost, the weight, and other potential operations that it has been subject to. And here, these are the final renders of these garments. Okay, well, these suggestions are pretty arbitrary. So next, I will show you, oops, this is again the same. The next video is about our other product, which is called Showroom, and is a tool to enable communication between mills and garment designers and brands. So right now, what is happening, what used to happen before, is that people, fabric mills that created the fabrics, attended these massive conferences, let's say, to sell their fabrics, and people came there and touched the fabrics and, you know, decided what they wanted to buy. Now, with the COVID situation, this kind of interaction has disappeared. So the problem of mills having to communicate what they have, what they provide, is a real problem. So there is here a huge business opportunity to find the appropriate tools to facilitate this communication. So let me show you a little bit of demo of the showroom product here. I think we can start here. No? Yeah, I think. No, here. Okay. So yeah, let me skip this. Yeah, so we provide this digital platform where the people can communicate about their needs, and we provide several visualization of the fabric, how they look on different predefined fabrics and garments. So here the brand might be able to change the color of the appearance, to see the fabric in context of a different garment or a different theme, so that they can compare and make a decision, a commercial decision. We provide information about the fabric construction as well as any other information necessary regarding optical or mechanical parameters. What we also provide is a tool to enable the creation of physically based colorways. Let's see if we have some results here. Yeah, these are the colorways. So the goal of this kind of tools ultimately is to provide some predictive tools so that the mills doesn't have to build all the materials. They can know in advance, if we put certain dye, how the material is going to look like. And this is the final goal of this product and of us as a company. Okay, I think I'm going to stop this. Okay, so that's it. Let me see if I can switch to the final presentation. Yeah, so here you have my email, my webpage, in case you can check about the research and you can try to explore a little bit about what we do. Also in the university, we do a lot of research in collaboration with the MS Lab group. So you can explore that too. And feel free if you would like to do an internship or you are looking for a job, whatever you want, just feel free to email me, and we might also provide some projects in collaboration with the HILAB group in the university. So yeah, feel free to contact me. So I think that's it. I thank you for listening to me. It was a bit long presentation. I hope you have enjoyed.
So yeah, thanks Elena for the talk. It's pretty impressive how you managed to have all that kind of stuff already working. I remember when you guys started that all that was almost like a dream goal, and you already have many things actually in place. So it's pretty impressive because the challenges for all that are enormous. So anyone who wants to ask some question, please raise your hand. I think Google Meet already allows to do that. And also Julio will be reading some of the questions that might uh, happen in the YouTube broadcasting. But in the meantime, guys, please don't be shy. Ask questions. But in the meantime, I will try to ask some. So Elena, so you guys have done quite a bit of work on capturing things, and you already fit in the material. Have you tried to compare how does this fit in this model, which, as you said, there is always some limitations on what you can on what you can model using path research, for example. Did you compare between the things that you actually capture with your capturing device and what you are able to simulate? And how close is that?
You mean if we have real pictures of the fabrics?
Yeah.
And yeah, actually, yes, we have. I didn't show it, but we have validation setup. This is what we call it, where we have the fabric is hung in several positions. I think I saw it at the very beginning for the mechanical parameters. So we hang the fabric in several positions that we know that they convey the drape. They are meaningful for understand the fabric. And yeah, we do that. We take a picture with a control setup, and then we try to replicate this setup in render and see if they match. Yeah, so this is what we have right now, and so far it's good. I mean, for render is easier. For simulation is a little bit trickier because the simulation depending on the initial state of the simulation, the drape can go one way or the other. And so there are more parameters that take place in that process. But in any case, yes, we are doing that.
Okay, so David has a question. So yeah, go ahead and ask whatever.
Hi, Elena. Thank you for your presentation. It was really impressive. One small question that I would like to ask, because I actually have two questions. One is related to the last video you showed, and it is you capture the materials and then you create the parameters. Do you have to capture different materials for different dyes or colors, or is it a transferable property and you can create like many different colors from one capture?
This is a very interesting question. Actually, right now the colorways that we are generating only requires one capture, because we take a look at the dye and how it has and how the color pattern has. But this is something that we do at the fabric level. In order to validate that, we would need to capture real samples for all the variations. But right now, and the idea is that we will only need one sample of the fabric to predict how it will look like with different dyes.
Okay, thank you. The other question is related to the software that you showed, and I guess that it showed really fast light transfer simulations. Is it done in cloud compute? Is it based on cloud computing? Or does the user need any accelerator or anything?
Everything is working on the cloud. Everything.
Okay, so
yeah.
I guess that it's hiring GPUs or like renting GPUs for the computing.
Yeah, so we use Amazon services for Amazon Cloud Computing Services. Sorry, Amazon no, Google. Google Cloud Computing Services, and we, depending on the demand of the computation, we can add extra nodes to the system if they are necessary. But everything it works on the cloud with all the problems and challenges that this implies, but yeah.
I have been merely related to that kind of infrastructure, so I kind of know how it works. And then finally, I would like to ask if the software right now has any integration or intention of integration with virtual reality. Is it something that?
Yeah, so there is, in principle, there is no limitation to visualize these renders with VR. We did a demo at the very beginning, and actually it was a very cool feature for the people. Actually, maybe it might be interesting to get that back, because yeah, in principle there is no limitation, because you see the render and then you can see the render with VR or not. There is no physical limitation with that. So, yeah, but at the moment it's not linked.
Okay, thank you.
So yeah, there is another question from Diego, who is asking, how do you manage imperfections in the fabrics when you capture them?
It's a very good question also. It depends on at which level we see the imperfection. No? If we see the imperfection for the yarn model, an imperfection might not be a problem, because the forward model will be in charge of render these variations. No? The procedural model, for example, might be able to generate these imperfections in a very controlled way. That's for the yarn model. For the surface model, imperfections might be a problem. And if this happens with textures, if you have a texture with something that has a mark or something, and you repeat it, you are going to see the imperfections. So we need to deal with them and remove them, or being very careful to not have these imperfections.
Isn't there more questions? If no, I have plenty. Or Julio, is there any question in the? No, we don't have any questions on YouTube. So. Okay, so yeah, so I can just continue asking. Yeah, you know that I'm like this thing. So yeah, I was wondering when you do the volumetric rendering with the path tracing, or the volumetric, the explicit micro level rendering, you are, I guess you are computing some relatively simple. This is CSDF, right? For the fibers, you are not computing something very fiber dependent in terms of these things that we did in our work with Carlos Aliaga et al. When we render explicit fibers, you are taking an approximate model, and that's the thing that you're using for fitting, right?
I might not be the best person to answer this question, but I believe what we have is a BSDF, like the one that I showed you in the render slide, where we model several bounces, like the T transmittance, the reflection, transmittance, reflections, transmittance thing up to 4 bounces. And then this data is, I don't know the question. Your question was if we are doing that analytically, the render?
I guess it's a parametric model, and then you are fitting the parametric model rather than using some from top to bottom. If you are doing a top to bottom approximation, that you are essentially fitting your parametric model instead of doing a bottom up approach where you model some parameters for some particular fiber. So you, for example, know that a silk fiber will look somehow like or behave their scattering somehow like this, and then you just fix that parameter in order to fit your model rather than fitting every parameter of your scattering.
So the fitting of the BSDF was done in a very coarse way. We had a real-time model which was similar to the path trace one. So we initialized the path trace one with the real-time one. And then we tweaked some of the parameters manually in the end. So this general model fitting is one of the greatest challenges that we still have open in this project.
Okay. No more. So Ismael is asking, how do you know how to implement fabrics from sequence? Do you do it? What is sequence? Ismael, maybe you can pick up and better than. Oh yeah, lentejuelas.
What? Say that again.
If you know how to model fibers with cloth with sequence with lentejuelas. I didn't know the word.
Okay. So in principle, a surface material model would allow you to render sequence, but they would be flat in the surface. You won't see the thickness. So our next step for improving this realism is to add this thickness so that we can actually see these effects, as well as we can actually see the flyouts and any other thing you can put on top of that. But you need to take into account explicitly these elements for render them. You need to either model them with geometry. You can use displacement maps or any other techniques to actually take into account the geometry. No, you need the depth.
Okay, thanks, Elena. So yeah, I guess if there is no more questions, we can call the day. We can. I want to thank you, Elena, again for the talk. It's pretty cool. Remember all that within the master you can do internships in companies, and if you are interested in what these guys are doing, you can just send an email to Elena to ask them for what projects they are doing, which, as you can see, there are many challenges ahead in both graphics, computer vision, machine learning, and I think even robotics. So yeah, thanks again for sharing some of the challenges you guys have and your results, which are pretty cool. and for your time.
Thank you, Adrian, for inviting me. It was a real pleasure.
So yeah, that should be a very sound clapping, but you know how these things work with virtual meetings. So yeah, thanks again, and it was great to see you.
Thank you, guys. Bye bye. Take care.
Bye bye, Elena. Thank you.